We will talk about static force analysis. There are two methods used in this course: free body diagrams and the conservation of power. This slide will show you how to use the method of free body diagrams to figure out all the laws acting to the mechanism under an external force of a torque. In order to determine the force acting on all the components of the mechanism, free body diagram of each component is sketched isolated from the mechanism, like this. Generally speaking, there are 4 steps to do free body diagram analysis. Step 1. You need to sketch free body diagram of each component of mechanism except for the frame. Step 2. All the force acting on the components must be indicated on the free body diagrams. For example, action and reaction forces between the components and the external loads. They may be force of a torque in applications. Step 3. You need to write down 3 equilibrium equations for each of its components. In this course, we only concern the planar systems. When the system is in equilibrium, we can get 2 force balance in the x and the y directions, and 1 moment balance about axis D. Finally, you need to solve the equilibrium equation to figure out all unknown forces. The details we'll be talking about later. Before using free body diagrams, we need to talk about transmitted force on the different types of the joints. In the revolute joint, there is a rotational freedom, and any moment along the axis of the revolute joint will not be transmitted from one member to the other, but there will be a force transmission in any general direction. In a coplanar system, that means the force have 2 components, x and y. Due to action and reaction, there are 2 bodies that are involved. When one body exerts a force on the second body, the second body simultaneously exert a force equal in magnitude and opposite in direction on the other body. In case of prismatic joint in a pendulum mechanism, there will be no reaction force component along the axis of the slide, but a force Fy perpendicular to the slide axis, and the couple ND along the lead axis will be transmitted between the links joint. Due to force of action and reaction, the forces and the couples between 2 links should be the same. Sometimes forces are at pure rolling contact. For example, a cylindrical roll pair. A roll rolls but does not slip on the surface on which it rolls. In this case, transmitted force include normal force Fy and the tangent force Fx. In a situation, forces are at rolling and sliding contact. A cam pair, for example, it permits translational and rotational motions. If we neglect the friction between the surface of the cam pair, transmit force is only a normal force Fy on the contact point in this case. We can show the force acting on an object using a force diagram. In a force diagram, an arrow represents each force. The arrow shows the size of the force and the direction in which the force acts. The arrow should be labeled with the name of the force, so we can use them to make up equilibrium equation of free body diagrams. The textbook gives a force convention for labeling the names of the forces. If the force is exerted by the member I and member J, Fij will represent the force. We can take a look at the free body diagrams of the member 2 and 3. Here, the revolute joint B connects member 2 and 3. Joint B gives action force to the member 2 and 3 both. A force acting on member 2 from member 3, we label it as F32. And a force acting on member 3 from member 2, we label it as F23. Due to action and reaction, we know force F23 and F32 are equal in size but acting in the opposite directions. Let us practice to label the names of the forces in free body diagrams first. This example is a vice grip plier. A pair of force FH are exerted by user's hand on the handles to clamp the object 5. In this case, the weights of all the members are negligible. This plier has 1, 2, 3, 4, and 5 members. There are 4 revolute joints A, B, C, and D. And the place of the gripping the object 5 have a pair of cylindrical lower pairs between members 5 and 1 and members 5 and 2. This figure shows the exploded view of the plier. Let us practice to plot the forces of the plier in the position. First, we need to check if the mechanism has 2 force members. We can see only member 4 is a 2 force member. So, if member 4 is in equilibrium, we know that the forces must act along the line between the 2 connection points C and D on the body. This means that the direction of the force vectors is given on either side of the body. Additionally, we know the forces are equal and opposite. So, we draw the force F34 acting along the line between the points C and D first. F34 is a force acting on the member 4 from member 3. It can be either pushing or pulling force. We assume it is a pushing force. If it is not correct, the force will be negative. The other force, F14, acts on the member 4 from member 1. It is equal and opposite to F34. Here, if the forces have the same size, their colors of arrows will be the same. Then we draw the forces acting on the member 3. Joint C connects member 3 and 4, so a reaction force F143 acting on joint C from member 4. F43 is equal and opposite to F34. The force F23 acts on the joint B. We do not know its magnitude and the duration, so we give X and Y components of the force F23. Let us see object 5. It looks like a ball in static. So each side have a normal force and a tangent force acting on it. In the equilibrium of the member 2, reaction force F32 acting on joint B4 from member 3, it is equal and opposite to F23, and a reaction force F52 acting on the gripping surface from member 5, it is also equal and opposite to F25, and a spring force Fs acts on the joint U. We know the force of spring always acts along with the spring. It means we know its direction. For the force F12 acting on the joint A, we do not know its magnitude and the direction too. So join two components X and Y of F12 here. Finally, if member 1 is in equilibrium, forces F51, F21, Fs, and F41 are all the reaction forces. We can draw those forces one by one, like previous days. I will explain FreeBody diagrams through a four-body mechanism. It is textbook example 14.2. In this case, all the waste of links are neglected. This example is a good fundamental problem. I think if you understand the methodology to solve this, although it may not be the exact problem you are facing, you can definitely extend these steps to solve other similar problems. So, as a mechanism engineer, what we like to do is to use computer simulation, ADAMS for example, but we have to be able to verify those results with hand calculations. So what you have here is you have an assembly of a four-body mechanism. Some key concepts you must keep in your mind. They will help you to figure out the problem systematically. First, I want you to identify two force members. We will go into detail what this is in the coming slides. Except for the frame, you need to sketch each member isolated from the mechanism and put all the external forces on each member. Thus, you can express the equilibrium equations of each member. We call this as FreeBody diagrams. If we have equilibrium equations of all members, they can make up a system of linear equations. So we can figure out all the unknown forces of this mechanism from these equations. Now we will talk about how to use FreeBody diagrams to solve static forces step by step. This figure shows a four-bar mechanism. This mechanism has four revolute joints. In this case, the external force F is 120 pound force at the angle of 220 degrees relative to the horizontal. Here, the input torque is unknown. We need to figure out the torque to select a proper motor of the mechanism. And the external forces acting on each component also need to be determined to design the dimensions of links for avoiding the mechanism failure. The first step, you need to identify two force members. What are two force members? Two force members basically have only two locations where forces act. So if you look at this assembly, I want you to think about which of these members are two force members. I will show you what it is later. In this assembly, a two force member is link 3. You can see there are only two locations on the member where force acts. Link 2 right here. You have two joining reactions and one input torque on this member. And then link 4. You have two joining reactions and one external force acting on it. So link 2 and 4 are not two force members. One question: why do we want to identify two force members? Because they can greatly simplify the free body diagram. You can see here, I broken these two force members out and drawn the reaction forces. If a two force members is in equilibrium, two forces are collinear and equal in magnitude, but in opposite directions. It means that the location and the direction of the forces are figured out on two force members. So that's really important to find two force members. Do that first. The next step, you need to draw free body diagram of each component. The mechanism is broken down into separate components, links 2, 3, and 4. You can see the exploded view in this figure. And then we need to draw external forces on each link. Let us start from two force member, link 3. We know this link have two reaction forces acting on it. These two forces are collinear. They equal in magnitude and opposite in direction. We draw the force F23 first. F23 is exerted by link 2 on link 3. Because the position of the mechanism is given, we can know force F23 acts on link 3 at an angle of the 22.75 degrees relative to the horizontal. This force may be one of two directions. We can choose this direction. If it is not correct, the force will be negative. We only need to flip this direction. In equilibrium, the force F43 is equal and opposite with the force F23. Let's see link 2. Link 2 is a two force and a moment member. Position A have a force F32 acting on link 2 from link 3. The force F32 and F23 are action and reaction. So we know that the force F32 is equal to the force F23 but in the opposite direction. The forces F12 and F32 from a couple which is equal and opposite to the input torque. Therefore, the forces F12 and F32 should be parallel, equal in magnitude, but opposite in direction. We already made sure that the direction of the couple is opposite to the input torque. So we can draw the torque T12 in clockwise direction like this. Let's see link 4. Link 4 is a three force member. Two forces acting on point B and B star, and an external force P on point C. The external force is given 120 pound force at an angle of 220 degrees. And the forces F3-4 and F4-3 are equal in magnitude and opposite in direction. For the force F14, we do not know its direction, so I wrote this force with X and Y components. Until now, we are well done free bodies of components of mechanism. Before going to the next step, you need to identify a member that you can solve. Let's take a look at these links. For each link, you have 3 equilibrium equations. So let's check this link and try to find which link can be solved. Let's look at link 2 first. We have 2 unknowns here. Although we have equilibrium equations, but we don't have a force value to relate it. Therefore, we cannot solve this problem. Link 3 have one unknown force, but not a force value to relate it. So we cannot also solve this problem again. Link 4 have 3 unknown forces and a given external force. Since we have 3 equilibrium equations of free body diagram and a force value to relate it, we can solve it this time. To translate the forces down the line from link 4 to link 3, then to link 2, we can solve the problem completely. So let's get started from link 4. The positions of all links can be determined through the position analysis. We know the 4-bar mechanism have constant lengths of the links. If input angle θ2 is 135 degrees, we can obtain the θ3 and 4 are 22.65 degrees and 68.65 degrees respectively. In the equilibrium of the link 4, we have 3 equations to solve 3 unknown forces, F14x, F14y, and F34. Here, a 120 pounds force P is applied at point C on an angle of 220 degrees, and the force F34 acts at point B on an angle of 22.65 degrees. RB and RC are the positions of point B and C related to point B star. Their directions are an angle 68.65 degrees, and the magnitudes are 12 and 5 inches, respectively. We write forces and the positions of points B and C in vector forms, like this. In a planar system, they have 2 components, X and Y. In this case, we select point B star as a reference point of the moment. We can get a moment equilibrium equation like this. The sum of RB cos F34 and RC cos P equals 0. In this equation, only F34 is unknown, so we can figure out the value of F34 is equal to 33.31 pound force. After that, we write 2 force equilibrium equations, in which there are 2 unknowns, F14x and F14y. They can be figured out for 64.18 and 64.31 pound force, respectively. You can translate the force F34 from link 4 to link 3. To get the force F43 is 33.31 pound force. If link 3 is in equilibrium, F23 equals F43. The force F43 is also 33.31 pound force. Again, you can translate the force F23 from link 3 to link 2. You get the force F32 is 33.31 pound force. Force F32 and F12 is a couple. They are parallel and in opposite direction. The distance between them is 5.52 inches. So you get force balance equation. F12 equals F32, and you can express a moment balance equation referring to point A start. Thus, T12 can be solved and is 184.8 inches pound force in clockwise direction. I give you a summary for the main focus of this presentation. The method of free body diagrams is broken down into 4 steps. If you remember this step, that's really helpful for you to deal with static force analysis using free body diagrams. First steps, let's go through to identify 2 force members. Why we do that? Because this will greatly simplify the free body diagrams. To broken down each of the assembly components into free bodies, and then to draw the forces of the reactions on each component. Then next step is to identify which component is solvable. You have 3 equilibrium equations in your pocket for each component. So you just really to find those components that you know you can solve for. And let's translate the forces down the line and you can solve the problem completely. In another way, you can also make up a system of linear equations by equilibrium equations of all components and apply these equations to determine all the laws. The last step is to flip the direction of the negative force vectors you solve. Following these steps, it will be easy to solve more complicated problems.